So yeah, I'm going to talk about interplanetary dust emission as a foreground for the LiteBIRD CMB satellite. So I have to admit, this is not really cosmology. It is more solar system stuff, but it's stuff that might be a problem. Not really, but it might cause a couple problems for LiteBIRD, which is a cosmology experiment. It's a cosmic microwave background experiment. And I'm happy to see Nobu is here. If I have any hard LiteBIRD questions, I'll send them to him. And hello, everyone else. So I'm going to start out with just talking about what is zodiacal emission. Some people know, but sometimes people don't know. Then I'll talk a little bit about LiteBIRD, and then I'll try to show how the zodiacal emission will show up in LiteBIRD. And in the end, I did this project because I have done a little bit of this for Planck. It was a little problem for Planck, and I wanted to make sure, because LiteBIRD is so much more sensitive than Planck was, I wanted to make sure that it wouldn't be a big problem for LiteBIRD. And I don't think it is. And LiteBIRD might be able to do something interesting with it. So I'll try to cover those. So on the right-hand side of this plot, you can see what's often called the Zodiacal Light, or sometimes the false dawn. This isn't really Gegenschein, but basically what you see here, this is a picture of Mauna Kea. So I thought these were heads at the beginning, but these are different telescopes. And this is the Zodiacal Light. And essentially the sun is below the horizon here, but there's a bunch of dust here. The sun light is reflecting off the dust, and that's what we're seeing. And that is zodiacal light, and is sometimes called false dawn. Gegenschein is actually, it would be much, in this picture, it would be much higher. It's actually at 180 degrees away. But it's the same idea. Most of what we talk about when we say zodiacal light is reflected sunlight. So that's what I'm going through here. I'm actually going to be talking about something else. So we're talking about cosmic microwave background. LiteBIRD is a cosmic microwave background experiment. So we're talking about really long wavelengths, a millimeter or even longer here. And reflected light, we don't really see that. But what does happen is that these grains here also absorb some fraction of this sunlight. They heat up, and then they re-emit that light. And that's in the submillimeter. And CMB experiments, in principle, can see that. And the question here is, will that be a problem for the LiteBIRD satellite? It was something that Planck detected. And so we want to be sure, or I wanted to be sure. This is not yet an official LiteBIRD project here. Okay, so let me see. I'm spending too much time on that slide. So just to recap this again, this is a picture of our solar system. Here's the sun, Mercury, Venus, Earth, etc. Here outside here, you have the Kuiper Belt and maybe even other galaxies. In between Mars and Jupiter, you've got the asteroid belt. And I don't know if you can see these little dots here, but these are actually supposed to represent interplanetary dust. There is dust throughout the solar system here. They think, and it's not really me, I don't do this, but they think that most of it comes from collisions among these asteroids and or stuff that's basically exhaust from comets. It's a field of active work because when the particles are really small, solar radiation and solar wind actually blows it out of the solar system. And if the things are too big, they actually spiral in due to Poynting-Robertson, I think, effects. But basically, it's a question, why do we still have dust here? So there are still interesting things we can do about this. There are experts in it. I'm not an expert, but you know, maybe on LiteBIRD we can help with the long wavelength and these observations. But anyway, the other thing I want to point out here, and I will point it out again, if I look at, say, this galaxy, when the Earth is here, I'm looking through a certain column depth, a certain column of this dust here. 3 months later, for example, when the sun is over here, if I look at the same region, I'll be looking through a different column. And that means that this zodiacal emission that we look at, it's actually variable over the year. And that's something that I was worried would be causing us a problem. And it does cause problems. It's not something insurmountable, but it's something that complicated our work on Planck, for example. So it's something that we have to keep in mind and look at. So as I said, this is thermal radiation. And so what I'm showing here is not the cosmic microwave background. These are maps from 5 to 240 microns from Kobe Derby. So these are infrared. These are real infrared, mid-infrared, and far infrared maps. And what I want to point out here, so at 5 microns, these are in galactic coordinates. So I'm going to change that. But for the moment, the galaxy is along the center. And then this sort of S-shaped thing, this is the zodiacal emission. And the thing I want to point out here is that it's kind of faint at 5 microns, but then by 12 or 25 microns, ooh, I wish this line wouldn't show up. But anyway, at 12 and 25 microns, it's the brightest thing in the sky on large angular scales. And then as you go further and further in wavelength, it gets fainter and fainter. So if you really wanted to study zodiacal light, you would look at around 20 microns, or an order of magnitude longer. Okay, excuse me. And here's something I got from an old paper, but it's still the best one to show all of these effects. And so what I'm looking at here is 0.1 microns all the way up to what, 10,000 microns. So this is a centimeter, basically. And the pictures I just showed you are essentially in the mid-infrared. Actually, you didn't see these, but these are the lines. This is 5 microns, 12 microns, 25 microns. So you can see the zodiacal light is really sort of at the 20 micron level. What we're going to be talking about is the cosmic microwave background here, say between, I don't even have the numbers in my head, but between 40 gigahertz and 400 gigahertz. And what that means, if this is the spectrum, if the peak is at about 20 microns, and then you start to see the tail in emission, we are talking about a really long extrapolation here. We're talking about detecting stuff way below the CMB, way below the galactic dust. And on one hand, that's really hard. And you would say, why do you have to worry about it? And the reason you have to worry about it is LiteBIRD is going to be so sensitive, or at least hopes to be so sensitive, that it could affect certain things down at the noise level of LiteBIRD. Let's see, what do I want to say? Yeah, that's about all I wanted to say here. So we're talking about a long extrapolation. This is not stuff that people usually worry about for the cosmic microwave background. Okay, where does this come from? This is a picture now of basically the cloud. And what you have to imagine here, this is the model we'll be using. And basically what we need to do is figure out where the sun is at each point, where the sun is, then where the earth is at each point. What is the density of dust around us? And then we have to integrate through a line of sight towards where we look at to get an estimate, a simple estimate of the emission that we're going to see. So basically around where the earth is, which is usually at 1 AU, so it's around here, this is 4 times the same thing. It's kind of detailed, but basically all you really need to know is there's a cloud that sort of looks like a torus of dust. And we're looking through this torus of dust. Around here, it's about 286 Kelvin. It's about the temperature of the Earth. And it gets colder and colder as you go away. And we have to integrate that along the line of sight, assuming a density model. That model we use comes from, this time, comes from the Kobe Kelsall et al. Model. So that's something that the Iras Derby people came up with here. There are also a couple of weird things. I'm going to go through them, but it's in general, the zodiacal light is a nice diffuse cloud But when it was discovered, there were some weird effects that I want to walk you through here. So basically, this is, excuse me, this is repeating what I said before. We have a cloud of dust in the solar system. This is supposed to represent the orbit of the Earth. So we're always observing from somewhere around this circle. And so if we observe from here, we go through a line of dust, basically, and we have to integrate over this line of sight to get the total signal. You can get exactly the same thing if you're on the other side of your orbit, and you're essentially looking through the same column. It's not exactly the same dust, but it's the same column. But if you, over here, for example, if you observe, say, through a different column here and a different column here for the same distant point, you will actually get a different signal. And this is what worries me a little bit, is because imagine I'm looking for polarization and my polarizers are oriented in one direction here. And then I look at the same part of sky, but I've rotated my polarizer. I will see a different signal. Because I've rotated my polarizer, I'll say, oh, that different signal must be polarization. But it is actually not polarization because I'm looking through a different column as well. This is a small effect, but it's something that we should check because that is LiteBIRD's raison d'etre to measure polarization here. So this is what worries me. Okay, as I said before, now in the CMB, the Zodi is mostly an infrared is mostly an infrared phenomenon. And so when we go to CMB channels, and this is even sort of sub-millimeter infrared, it's not even real CMB. When we go to 857 gigahertz, if you look at this map, it's almost all galaxy here. You don't really see any Zodi. If you did, you should see it about here along. This is the ecliptic plane. And what I've done here is this is a map made from the first 6 months of Planck data. And this is a map made with the second 6 months of Planck data. And you really don't see anything. But if I subtract these two things, you get this map. And this, at least for me, this encapsulates everything we're trying to do here. First of all, the signal, the zodiacal signal looks like this. It's this blue part, and then this red part, and then there's sort of a red part and it's confused with the galaxy, and then there's this blue part. That's actually the difference Zodi signal because of the way we observe things. It's variable in each of these two surveys. So in this survey, it's a little brighter in this region than this survey here, and that's why we get the blue. But here, it's a little brighter than here, and that's why we get this red, etc. That's all fine and good, and honestly, we detected this, and we can make a good measurement of it. And that's not the thing I'm worried about. The thing I'm worried about is ultimately, we needed to really remove this. These are the effects of our far side lobes. When we observed in a certain region here, the galactic center was closer to our beam, but still many degrees away, but closer to our beam, certain parts of our beam, than in this survey. And we ended up with this big effect. These are our far side lobes. These are imperfections in our beams. They're hard to remove. You only see them sort of once a year. And so it's really difficult. And even they are much fainter than the galaxy and the CMB anisotropies. And this is the whole game that I'm worried about, is ultimately for any CMB experiment, I'm wondering about Simon's as well, actually, on some level. But we want to be able to remove this. We want to be able to remove this. This is actually a different part of our side lobe problem. Stuff like here, this emission is I think this one comes from variable calibration a little bit. So over time, things vary. The point here is this Zodi can make the rest of the analysis more difficult as well. And ultimately, I think that's the point I want to get across is we'll certainly see it. We should be able to remove it, but it will complicate things a little bit. So that's what I want to say, as it did for Planck. And this is another way to look at this. This is one of the ways I look at it. What I've done here is I've taken, there's a project called Beyond Planck that looks at Planck foregrounds a lot. And they have a dust map. And I've basically just taken 10% of their pixels that are away from the galaxy. And I've just plotted their spectrum over Planck HFI regions. So that's from 800 gigahertz to 100 gigahertz. So this is real data that's been processed. And I go from about 20 degrees away from the galactic plane where it's brightest up to the galactic poles here where it's faintest. And then I use this model of zodiacal light and I plot that. And the fact that the brightest zodiacal regions overlap with the dimmest, basically coincide with the dimmest galactic regions, make me think that we are confusing on large angular scales some of the brightest zodiacal emission with some of the dimmest galactic emission. So again, we're making this ZODI could make it difficult, because it's variable, to remove galactic dust at the lowest levels on the largest angular scales. And most people who know what happened with the bicep, for example, this can complicate that as well. So I think I've motivated it. So those are my motivations for looking at this here. And that's what I wanted to talk about for the zodiacal light in particular. Now I want to talk about LiteBIRD. I've just got 2 slides on LiteBIRD. This is not an official LiteBIRD talk, but I do want to highlight that there is a very good paper now. One of the reasons I'm doing this right now is that the LiteBIRD has a series of SPIE papers that came out recently, and really they give you all the information you need to do these simulations. Before these papers came out, I didn't have all the information I needed, and now I do. The important things to note is that it is a Japanese-led satellite, but there is certainly going to be European collaboration, and there are proposals for American collaboration. It's polarization over the full sky. Baseline is 3 years for the mission. It will observe from the sun, the second Earth-Sun Lagrange point. And wow, I really hate this bar that keeps getting in my way. Basically, it will also observe in 15 bands from, I don't know if you can see this, but from 34, basically 40 gigahertz to 400 gigahertz here. So it covers a lot of the Planck region, but not all of it, honestly. It covers, yeah, okay, there we go. And it's, I think the official launch date is late in this decade. The last I heard was around 2029. Let me see. I think that's everything I wanted to say. I'm going a little too slowly. Okay, and so one of the things that I needed to do here is really just make a simulation of the LiteBIRD scanning, and it's complicated. It's more complicated than the way Planck scans. It's similar to the way WMAP scans, but it only has sort of one. It's not doing differencing telescopes. It only has one. So essentially, the Earth, the anti-sun axis goes slowly around the sun. Then we have a spin axis that rotates around that spin axis and continues to do that as the Earth goes around the sun. And then there is another level of spin around this spin axis. And even on this bore site, there's a half wave plate that's spinning around here. Okay, and so what this ultimately means is that we're looking at each point of the sky with a lot of different angles, which is what you need for polarization. As I said before, it's going to be a 3-year mission. This spin is every 3.2 hours. This spin is every 20 minutes. And the half wave plate spin is 39 revolutions per minute. And the detectors themselves are sampled at 19 hertz. I don't have the computing power or the the will to simulate all of the detectors. So I just simulated one detector at each frequency and try to make extrapolations from that. Let's see. Okay, and the last element that I wanted to put in here is this model is really not very good. It's really old. It was created in the 90s when people had computers that had literally thousands of bytes of RAM instead of megs or gigs or anything. But it's the best thing that we have, and the reason I'm using it in particular. Most other models are calibrated in the infrared, and we need something that has been calibrated in the CMB. And so because basically I did this for Planck, I can extrapolate the model. These are the different components that we're talking about. I can extrapolate this to LiteBIRD wavelengths, whereas with all of the other models, I really don't know how to do that yet. And that becomes important right here. I just want to show this. If you become interested in this, one of the good papers is this recent Gigahertz paper that talks about it has a model that's well calibrated in the infrared. Somebody should extrapolate it to the CMB. I don't have the strength to do that right now. The thing I want to point out is it does make a big difference. This is the model we're using. This is the Kelsall model, and these are maps at CMB frequencies. These are maps at sort of far infrared frequencies. I want to point out the scales are just really different, right? So this is something that has been calibrated at the Planck end, but it has not been calibrated, and they get vastly different numbers for estimations of what we should see in the Zodi. So this is just to underline that these models are not very good. There's a lot of work we can do to make them better. This is just a first try to check if we're at the right order of magnitude so that it doesn't cause a huge problem for LiteBIRD. But there's a lot of, that also means there is science that can be done here as well. Let me see, so I might have to speed up. So I go through and I do all of this simulations, and instead of doing 15 different bands for thousands of detectors, I did 3 bands with 1 detector each using the ultimate sensitivity. This is the highest frequency band on LiteBIRD, so 402 gigahertz. This is, now I'm in ecliptic coordinates. So this is the ecliptic plane. I've represented the galactic plane here with these 5 gray lines. So this is where it's brightest. These are in micro K CMB. So even at the highest frequency channel, it's not that bright. It's comparable to the CMB anisotropies. This at 120 gigahertz is essentially the LiteBIRD's most sensitive channel, or one of the most sensitive channels to CMB. And we can see that there's going to be 4 microkelvin here. For something like Planck, that's not that big, but honestly, that's bright for LiteBIRD. So it will certainly detect it. I'll show that again. And even at the lowest frequency channel for LiteBIRD, that's 40 gigahertz. It's essentially radio, as far as I'm concerned. That's still going to be detected. So these are the temperature, and you might want to ask, what in the world are these lines here? And I think I will talk about that on this slide. Yes, so what are these lines? I think this was the coolest thing I learned when I started looking at Zodiacal Light. So most of the time you just see one big band. That's not what I want. One big band, but then you start to see these lines within this band showing up. And when these were discovered by Iras, these are called the Iras Dustbands. And I just thought they were really cool. I was not around then, but if they do a lot of filtering and they look at the center, they can see separate bands. And there are basically 3 of them that Iras and Derby have seen. And you can say, what in the world causes these things that are essentially straight lines in ecliptic coordinates? And it took them a while to figure out what these things were. But essentially, you can imagine, so here's the sun, here's the Earth's orbit or something's orbit. And you can imagine that you have an asteroid, or actually 2 asteroids, going around, and suddenly they will collide. Okay, and so you'll get a lot of different parts, but essentially they have the same orbital speed, maybe with a little bit different. So what you end up having is going from two asteroids after about 10,000 years, because of the differential velocity, you end up having a ring of dust along the original orbit. And then after a few 100,000 years, every time it goes by Jupiter, it sort of changes the phase. Basically, it ends up filling out all possible orbits here. And so what you end up with is this torus. So this would be the maximum of, you'll have certain amounts of dust going in this circle, and then a circle next to it. Basically, the phase changes, and it fills out. And in the end, you end up with this whole torus of dust. It is literally a cylinder of dust, and the dust actually spends most of its time at the extremes of these orbits. And so this is really weird, but we actually detect it. And you see the extremes of the orbit because from your line of sight, the dust spends more time there, basically. So these are known as the Iras Dustbands, and it is a really cool little dynamical effect in the solar system. And it also means that these dust particles might be a little different from the rest of the dust particles. And the reason we see them better is because they're larger dust. They haven't been ground down after millions and billions of years. And so they're larger and they can emit at longer wavelengths. And that's essentially what we think we are seeing here. And that will be a big issue for LiteBIRD because we don't see the general cloud nearly as much as we see these rings if these estimations are correct. Okay, so that's the neatest little piece of physics that I've learned doing this. So these were the temperature, and these are estimations of the polarization. And it's really just noise. Basically, there is no intrinsic polarization assumed in these in these simulations. It's just the wave plate is spinning, and it depends on what angle you're looking at when you look at a certain point at one time of the year and another time of the year when you make the map. And that's why this just looks like noise with the basic Zodi envelope here. And you got to look and you got to say, wow, these are really low numbers, right? This is 30 nanokelvin here. But we're talking about very sensitive experiments, so we have to look for it, and so we have to look at the power spectrum. So the first thing I do is look at the 402 gigahertz power spectrum. So this is a dust monitor. This is not a CMB prime channel. And what I've got plotted here, these are the theoretical CMB anisotropies in gray, this line here. You can even see the cosmic variance here. And these points are the power spectrum of that 402 gigahertz map I showed. The point is, the Zodi is smaller even than the CMB anisotropies. It's smaller even than the cosmic variance here. So that's not surprising. At 400 gigahertz, it's not going to be a big problem. But this line is the sensitivity from LiteBIRD. This is the noise limit in the power spectrum. As far as noise is concerned, this is a huge signal. This is going to be detected with many in temperature here. And so therefore, there are going to be, maybe not the CMB anisotropies, but there's going to be other studies like dust, like other things that this might cause problems for if you're trying to get down to the noise level. For polarization at 402 gigahertz, there's a tiny bit of extra noise, but honestly, it's much lower than the experimental noise. Yeah. So at 402 gigahertz, we're going to have a good tracer. We're going to detect zodiacal light. So this is 119 gigahertz. So now this is the CMB channel. This is where we want to be sure we don't have any big problems. In temperature, once again, it's much lower than the anisotropies, but again, it's much higher than the noise floor. So this is going to be detected as well. Maybe not at the highest smallest angular scales. But this is going to be detected. And if the Zodi is not polarized, it's not a problem even for our B modes. This represents E modes. This represents B modes with R of 0.1, R of 0.0, and honestly, this is the LiteBIRD target of R of 0.01. So if this estimate is good, this variation, this extra noise, won't cause a problem for the B modes here. This is as good as LiteBIRD should be able to do. And one of the things I found amazing at 40 gigahertz. So this is, we're talking about centimeters, something like that. This is radio. We can still detect, there's this point, this point, this point. We can still detect the zodiacal emission. So we can detect this infrared thing in the radio, which is pretty amazing. It's a testament to the sensitivity that LiteBIRD is shooting for. And again, there's no problem with the polarization. So that's good to know. To continue, now I wanted to look at what about what science might we be able to do? And so there's a question. I've assumed up until this point that all of the emission we see is completely temperature, non-polarized, and just that we see extra polarization noise because of the way we scan and the way because of the way things change with time. And so here I want to look specifically at maybe polarized signal. So Derby detected about 10% polarization in reflection. So that's not what we're looking at. But I have never seen any thermal zodiacal emission polarization detection. ISOCAM, which was a 1990s experiment, set a limit on the polarization at 15 microns, I think, at about 1%. So we can say that the upper limit on polarization is about 1%. I tried to do something with Planck, and I couldn't set any sort of limits. It was non-informative. But there are mechanisms that might give us polarization. You can imagine if you have dust particles that look like, I call them M&Ms, I think you call them Smarties maybe, but just or ovalish things. If you're in a uniform radiation field, they're all going to be at the same temperature no matter what the orientation, face on, edge on, or side on. But if you're in our solar system, if the sun is always illuminating particles from one side, and you have to imagine that we're observing outside the plane, we are observing this system as we're observing the screen, there will be some particles that look colder. The ones basically that are edge on to the sun will be a little colder than the ones that are face on to the sun. And if they are longer than they are wide, those hotter particles are going to give us a net polarization, perhaps. And so this is something that Onaka at the University of Tokyo actually has pushed for ISO. He had a lot to do with ISO measurements here. And it is possible to get something polarized from this. So there's no, oh yeah, I should have said that one of the reasons it's hard to imagine polarization in the solar system is the magnetic field is totally different from the galaxies. You don't get alignment with a magnetic field in the same way you do with our galaxy. So you have to imagine other ways of creating this polarization. There is a magnetic field that changes in the system. So this is a mechanism. Onaka says that he could imagine 1% polarization here. So we're looking at 1%. So these are the same maps you saw before, where you just have this noise. And then in the next one, I show that we have what happens if I assume there's 1% polarization in the dust. So this is what we have if we assume there's no polarization. And then what happens if I make some assumptions about, I say there's perhaps 1% polarization in these particles, and then I also have to make assumptions about where we're observing from. There's a lot of angle. There's an angle you have to choose. I think I made a reasonable choice here. It's in the plane. It's in the plane of observation, basically. So if you do that, you do see a signal. It's still not a huge signal. So I haven't changed the scales here at all. But it's certainly, we start to see a signal. And this is something we might be able to look at. So here, this is, what do I have here? Yeah, so this is how these power spectra change that I showed you before. And the point is now with this polarization, the temperature hasn't changed at all, really. But now the polarization, there is something polarized that we should be able to detect. So I thought this was interesting. What I'm saying here is that LiteBIRD, which is a CMB radio mission, should be able to set limits, the best limits on the polarization of the zodiacal light that have ever been made. Honestly, if my assumptions are correct, which is pretty amazing given that the peak of the zodiacal light is in the infrared. The zodiacal light emission is in the infrared. We're saying that LiteBIRD is sensitive enough to actually set, world-class limits on the polarization. I think what this means is you need something like Spica to be funded with the polarization experiment on it. Anyway, so that's at the 400 gigahertz. So that is, again, that's our dust monitoring channel, and that will have a good detection. This worries me a tiny bit. So what I'm saying, you can see a couple points here. What I'm saying is, if the zodiacal emission is polarized at its, basically just below its limit today, the power spectrum from the Zodi will be comparable to the power spectrum of the CMB anisotropies at the limit that LiteBIRD is shooting for. So this is something we have to keep our eye on. I don't think the Zodi is polarized at its upper limit. That would have meant that ISOCAM, the old experiment, just barely missed it. I think it's probably much lower, and if it's much lower, then we won't detect it here. But this tells me that we really have to keep an eye on the zodiacal emission, and that's what I plan to do. And then at 40 gigahertz, it's not a huge problem here at all. So this is another one of one of my takeaways from this is that, we should be careful. It's probably not a problem for polarization, but we should be careful. And then ultimately, the real thing I'm worried about is what I was talking about right at the beginning, is that these are Planck maps, but if you look at LiteBIRD maps, you're not actually going to see the zodiacal light in it. The CMB anisotropies and the galaxy are much brighter, but we already know we have to remove that, and there's all kinds of great technology for removing these things. There are whole ERCs and grants for trying to figure out how to get rid of galactic emission. For the zodiacal light, we can use the variability of the signal and make clever difference maps. But then what it might end up meaning is that it's going to be harder to calibrate certain parts of our instrument. And that's what worries me the most, probably just because that's what I like doing the most, is trying to understand, characterize, and calibrate the instrument. And the zodiacal light is at the level where we want to calibrate our instrument, and it's variable, which is a crummy combination to have there. And I think that's probably all I wanted to say. So one of the big questions 5 years ago, when LiteBIRD and CORE and other experiments, well, actually it's important for Simons and S4 as well, for CMB experiments, should we have a wave plate or not? Should there be a half wave plate to try to modulate the polarization to help with usually ground-based instruments, say, to help with atmospheric noise? What I want to show here is this does wonders for zodiacal light as well. So this, you've already seen these two pictures before. This is the 119 gigahertz Q map, assuming that there is no polarization in it at all. And this is the power spectrum, and we said, everything is fine here. Now, if I turn off the wave plate and do exactly the same simulation, so remember, there's no polarization in this. It's just noise from the variability. I see, has somebody written something in the chat here? Oh, okay, that was you. Okay, so there's no noise in this simulation, but this is what whoops. This is what I get if I turn off the wave plate. Now, everything changes, and I'm cheating here, so I'll explain how I'm cheating. But the first thing I want you to note is that for this one detector, we have the wave plate cleans it up by an order of magnitude right away. Okay, and that's important, and that's really good. And then if we look at the power spectra, we go from something that's not a problem at all to something that is actually a problem for getting at the B modes. Okay, so I think it's good. This has been a question for a lot of experiments. In this case, I think it's good. The thing I want to underline here is that I'm cheating. And one of the ways I'm cheating is that I've only done one detector here. If I had another detector, say I split this in just the two and I oriented it at 90 degrees from the first detector, this map would actually be minus the original map, right? The reds would be blue and blues would be red, just because the orientation is different. And if I add those two, then I get 0 again. So that will help as well. But then you get into questions about, oh, do they have the same band passes? Oh, is the calibration okay? So you get back to the same question of, oh, wow, this might make characterizing the instrument more difficult. So all I can say is from a zodiacal light point of view, it's really good to have a wave plate here. And I really hope it works because it's also a hard thing to do. Okay, so I think I'm done. Yeah, so here we go. The summary, I'm just going to repeat some of the things I hope I said before. LiteBIRD should be able to detect the emission in every one of its bands, and that's impressive. It's not an infrared experiment, but it's going to really characterize over the full sky an infrared thing. Yeah, and in particular, we may be able to say something about the size distributions of particles, and especially the larger particles that are in the cloud. LiteBIRD will probably, I think, will probably set the most stringent limits on polarization of zodiacal emission ever done, which again is just amazing to me. And then this is what I wanted to highlight. I don't think it's going to compromise the CMB. We might have to model and remove it some. The biggest effect is that it's just going to make life a little harder, reducing the data. And then I did like the idea. The wave plate will help. I just really hope it works because it's a difficult thing to do. And I think that's everything I wanted to say. Thank you.
Hi, Ken. Yeah, thanks for a nice talk. I was just wondering, what about T to E or B leakage from the instrument? Would that be a problem for this?
It's wrapped up in here. So I think the T to E leakage is going to be a bigger problem for the galactic emission. But it does sort of come in here, right? So imagine that we didn't have a half wave plate. What we would have to do is start to we would have to co-add a bunch of data from a bunch of these kinds of maps with detectors at different orientations. Mm-hmm. And then, so at that point, you start to worry, are the two, if I co-add two maps, for example, if they're not perfectly calibrated, one to the other, then you will get T to P leakage when you start to do this co-addition. And so what this means is this puts a limit on how well combining different detectors you can do. I don't know if I'm being clear here. So it comes into this, basically I'm really happy we have the wave plate because the wave plate lets us do a lot of these things detector by detector. And that lets us avoid a lot of these leakages, actually.
Okay, so you're saying basically that the leakage from galactic emission will probably be worse. You'll see it first before you see the leakage from
Oh
the
yeah,
zodiacal.
I didn't put it here, but the zodiacal emission, basically, this is what I should have emphasized here, right? Galactic dust is just always going to be much brighter than the Zodi, except in a couple different regions. So if you're talking about straight up leakage, you're going to see it from the galaxy far before you see it from Zodi. The thing about Zodi is there are going to be some things that appear to be variable. So the galaxy isn't going to be mostly isn't going to appear to be variable, but the Zodi might appear variable. So at the lowest limits, you might see some weird things.
Okay.
After you've removed all the galaxy.
Okay.
So that is a really good question. So it does, it basically, these are spheric, they're cylindrically symmetric, right? So the ecliptic plane in this picture, the ecliptic plane is much brighter than the poles here. Even at the poles, it's not zero, but essentially, if I'm looking anywhere at this ecliptic latitude, I'm going to see pretty much the same thing. I think that's the question. So it does depend on the ecliptic latitude. If I make a scan up and down, basically in these plots, I'm going to see a nice parabola here. If I look here, I'm going to see a two-humped, I don't know, a camel or something. But if I scan like this, I actually won't see a big problem. And actually, that's an interesting point, because I when I first tried to look at this, I tried to look at the for bicep. I wanted to see if this would be a problem for the bicep experiment. But the basic point is they have a patch that is pretty low, so it's pretty far away from the ecliptic plane, so they don't see much signal anyway. And they end up doing a lot of filtering. They scan sort of back and forth like this, and they filter it out. And because it's so constant along each one of their lines, basically, I don't think they see anything. It gets filtered out. So it does depend on exactly what patch, but it really only depends on the ecliptic latitude. A more interesting question than bicep is going to be the Simons Observatory, because they're not at all doing that. I've been hearing that they will be looking much closer to the sun, which means that the signal will be brighter in general sometimes. And from what I've heard about I just joined Simon, so I should know more about this. But and I do plan on following this up. But they're getting close to the sun and they move around a lot. And this could make the Zodi variable and difficult to find. So I want to follow that up. Again, I don't think it's going to be the biggest problem. Galactic dust is always going to be the first thing you have to deal with. But there might be something that Simons has to work for the SATs. For the LATs, I'm not worried. For the large angular scale stuff, there might be something to look at or to keep in mind. For the small angular stuff, I don't think there's a problem at all.